appreciate the invitation. I'm really sorry I cannot be with you in person. Hopefully, maybe in the next year or so, I hope to finally be able to visit China and to meet all of you in person. And again, my apologies. I really, really wanted to be at the conference. So the work I'm going to tell you about is sponsored by Vanitech, our colleagues and friends at Vanitech. As well as, and we've had a lot of help from CISRI, from Dr. Yang Kai-Fu's group, in sharing a lot of data specifically to, relevant to China. So the people that have worked on this project are here, mostly PhD student David Santos did a lot of work, and Pranav Pradeep Kumar. And this is a collaboration between the College of Science and the College of Architecture. And if you have any questions, I encourage you to email me or connect on Twitter or any other way. We're happy to answer questions. So I want to talk a little bit about role of vanadium technologies in decarbonizing construction. This is a huge problem, as you know. There were some beautiful talks I saw on the schedule. So vanadium is, we call it the green metal because it is hugely important for enabling the energy transition. And it's one of the strategic minerals designated as a strategic mineral by both the EU and the US. And the versatility of vanadium chemistries is enabling many applications that are reducing CO2 emissions in the construction industry, as well as in things like the battery electrode materials, advanced high-strength steels for auto applications, vanadium redox flow batteries. There's a whole lot of range of technologies. And sometimes these technologies are in a little bit of a conflict. Sometimes there's great opportunities to enjoy some synergies across different industries. So I'm going to try to give you a brief perspective of what we've been studying. And really part of the idea is that benchmark assessments of critical materials are urgently needed to inform public policy so that we can expand access to vanadium and make sure that we have a supply of vanadium, both for old industries as well as for emerging new markets, many of which are really just coming up on the horizon, especially in energy storage. So vanadium essentially has a critical role to play in the energy transition moving forward. I wanted to start by talking a little bit about the role of vanadium. Many of you are very familiar with this, but just in case this is not something that you have seen before, more than 100,000 metric tons produced annually. It is very deeply connected to the steel industry. Most of vanadium is produced as a byproduct, as you know, during steel production. There are some primary vanadium mines that are going online in Brazil and South Africa, and hopefully soon in Australia and in China as well. So vanadium, this is the outlay for how vanadium usage currently is. You can see a massive amount of vanadium goes into steel. Some of it goes into titanium alloys, mostly for aerospace applications, some of it in the chemicals industry, and an increasingly large share goes into energy storage. Primary production of vanadium is still kind of small. Co-production with steel is very large, and secondary production is over here. But this also will be changing as more and more countries get on the map. China has pretty large vanadium production, Russia, South Africa, Brazil, but there are many more countries coming on board, including Australia and Finland and Kazakhstan, which will have a lot of vanadium production as well. And three biggest use areas right now: construction steel, automotive steel, and redox flow batteries. Those are probably the biggest areas. I'm going to talk about mostly today, given the scope of the conference, I'm going to focus mostly on rebar and steel section. I'll spend a little bit of a qualitative discussion on automotive steel, and if I have time, I'll go over very quickly some data on VRFBs. But this is about 90% of all vanadium production. Okay, so but to take a step back, why do we care about this? So it's the 40% problem is what we call it in the United States. The fact that the built environment consumes about 40% of all energy. more energy than industrial or transportation. And this is a number that has not gone down, despite worldwide about 30 to 40% of energy usage is from buildings. And it's not really been something that has been easy to tackle. And in the US, buildings are 72% of electricity use, 36% of natural gas use. So this is really a large challenge.
Now, it's no surprise that
and I'm going to show this here, the impact of the construction industry. 2.6 billion tons of CO2, 3.3 billion tons of CO2 goes into buildings, and
now it's no surprise
so
that
you can see here that concrete has. Give me 1 second. I had some audio feedback. I'm going to get rid of that. Okay. Right. Okay. So you can see this here, where you've got the impact of the construction industry is very, very substantial. A lot of it is all of the steps in concrete production, as well as in the steel production, right? So a big part of the energy consumption comes from embodied energy. A chart that shows that the biggest impact on carbon footprint and embodied energy comes from the
Hello, we couldn't hear you. Hello.
Give me 1 second. I think my Zoom
Now it's
crashed.
okay.
Okay. Okay. Sorry about that. Okay. Okay. So I don't know why the Zoom crashed. Okay. So the biggest impact on carbon footprint and energy, embodied energy, is coming from the materials that are used, the choices there. Concrete is a big part of this. The concrete industry is one of the biggest. It's responsible for about 5 to 7% of global CO2 production, and from quarrying and transport. And so one of the ideas that you can see here, construction related spending accounts for 30%.
Hello. Okay, let's wait a moment. Hello, Dr. Sarbajit, Banerjee.
Yeah, sorry, I don't know why it keeps crashing.
Okay.
Can you hear me?
Now it's okay.
Okay, can you see my screen?
Not yet.
Okay, let me share. I'm getting, okay, all right, okay. Give me 1 second.
No problem. Take it easy.
Yes. Okay, give me 1 second and I will share. Okay, from current slide. Okay, so concrete is a big carbon sink.
We couldn't see anything.
Is it working now?
Now it's okay. Now it's okay.
Okay, so concrete is a big carbon sink, and this has been a big part of this. 13% of the world's GDP is tied up in construction, but the productivity of the sector has only increased by 1%. So this is a real problem because of slow innovation in materials automation and manufacturing, right? So steel emissions are also very large, as many of you know very well. This is a huge problem, and it comes from the feedstock, the preparation of materials, iron making. And what we've done a lot of work on is life cycle assessment, a systematic analysis of the environmental impact We've carefully selected the system boundaries as per ISO standards, defined functional units, and performed an inventory analysis. And we've had a lot of help from Vanatech member companies, and Vanatech is acknowledged here, and from CISRI on coming up with the sort of deep dive into data that is needed to come up with good numbers. And then we've quantified the impact of each of the categories, considering the entire process of steel production and recycling across the board. So this is our overall framework that you can see here. We start with some structural modeling. We are looking at different types of structural steel, either rebar or steel sections. We are looking at vanadium incorporation and how by incorporating vanadium, you can look at different grades of steel, and how steel by vanadium microalloying, you can save on the amount of steel that is required, and then quantifying the savings in concrete and steel in terms of embodied carbon, embodied energy, as well as embodied water. And then we can essentially come up with a full framework and assess the impact of vanadium microalloying. So to take a step back, why do we do microalloying? Again, many people in this audience are very familiar with this. So the reason we do vanadium microalloying, it strengthens steel through formation of nanoscopic precipitates of nitrides, carbides, and carbonitrides during the austenite to ferrite transformation. And grain refinement is also something that you see during the ferrite pearlite transformation. And the effectiveness is really a very beautiful thermodynamic property from vanadium, the excellent solubility of vanadium inclusions in austenite as a result of the enthalpy of mixing means that you have a lot more miscible vanadium in solution prior to rolling, and you can work at some pretty reasonable temperatures as well. So this is really the reason for using vanadium microalloying. So one of the things that we did is we actually mined the literature, because as you know, there are many different types of compositions. Each mill has a different composition. Each mill has a slightly different feed ratio. So we came up with a machine learning model where we fed a lot of literature in the primary literature on rebar or steel sections. And we were able to come up with some models correlating steel composition and yield strength. So at different concentrations of manganese or nitrogen, we could come up with a multi-dimensional model so that we're not using just the ratio for one company, but we are using it across the literature, right? So what are the consensus values? And we actually come up with numbers that are pretty close to some numbers that Vanatech has reported previously. So this is from data from Dr. Glodowski, and who is a consultant with Vanatech at different nitrogen concentrations. So we come up with a pretty good agreement with these numbers. So once we have a functional unit correlating vanadium composition and other concentrations to steel the tensile, the yield strength, we can then do structural modeling, both at the level of single structures as well as entire building level structures. And we can figure out the savings in structural steel in terms of vanadium microalloying. So one of the things that we find from here is that we get about the 61% savings in steel from using 500 megapascal steel in rebar as compared to 250 megapascal steel, right? So this is pretty large, because you can, by using 500 MPa steel, you can design the building very differently and still have the same load-bearing properties, seismic resilience, but use much less steel and much less rebar, and that can translate to significant savings in carbon emissions. So we do account for CO2 emissions associated with vanadium production. We have some pretty good numbers on vanadium production. I have to also point out that these numbers are relatively large here, 32 to 39.1 kilograms of CO2 per kilogram of vanadium production. This number is rapidly decreasing as our vanadium manufacturers adopt greener methods for extraction. So this is in fact going significantly lower, down to even single-digit numbers for some of the new vanadium facilities coming online. And so as a result of simply rebar, if you extrapolate these numbers, and I'm going to go show some specific case studies, if you extrapolate these numbers and you complete this entire framework, just to be brief, we can show that vanadium microalloying, even though it's a relatively small amount, less than 1%, results in about 0.38% global reduction in the total fossil fuel carbon footprint. And this is a lot of this is coming from China.
Now, I understand that ultimately,
so a lot of this is coming from China because we see, one second, audio feedback. Did I get rid of that? Can you hear me? No. Okay.
Now it's okay.
Okay. Okay. All right. Perfect. Okay. It was going okay for now. All right. So, okay. So, something that I think is really exciting. If we look at the use of vanadium rebar in China, most of you know the story very well. 2008, the Great Sichuan earthquake. This is, led to a series of changes that have really had a massive impact on the worldwide vanadium market, and of course the Chinese rebar market, right? And so this has led to, but one of the stories that I think is really interesting is that because of the changes in Chinese rebar policy, not only has the quality of rebar improved, but we are also seeing significant improvements in CO2 savings in CO2 footprint. So this is a complicated graph, but I want to show a timeline of all of the events and all the different codes that have been implemented in China. And you see the prices of vanadium here per kilogram, and that has fluctuated a lot because of these design codes coming in. And you can see that in blue is the vanadium rebar, vanadium consumption for rebar in China really increasing massively from 2005 to 2019, right? In blue, from just a few thousand tons to really, almost here, very large numbers here that you can see for almost about 60,000 tons. And the global vanadium production is shown in orange, and you can see how much the Chinese rebar production is increasingly capturing a large part of the market. And if you look at the details here, each of these correlates, the price spikes correlate with the implementation of the new rebar standard, and before that, the previous guidance on grade 3 rebar, right? So vanadium supply, demand, and market price has really fluctuated with historical building code changes. Much of this is driven by China, but this has also been a huge driver for the vanadium industry across the world. And this is a great thing. You can see here, as a result of code changes, grade 2 and grade 3 rebar, dark blue, almost completely being phased out, and grade 4, grade 5 rebar is increasing slowly, and this is again driven by the building code changes and the new building policies, right? And an unexpected but positive consequence of this has, because by using higher quality rebar, we're seeing massive increases in the savings of carbon, because you're having to use much less steel, less concrete. And so really compared to, if we had compared to a baseline situation where, let's say, nothing had changed, there's almost a 2000% change in CO2 savings over time in the last about from 2005 to 2019. And the 2019 savings in CO2 are about 1.5% of the total rebar of the total CO2 consumption. So if you look at this, 230 million metric tons of CO2, this is a very large amount. And these are some ways to benchmark it. about 50 million passenger vehicles per year. If you can think about the volume of the savings here. This is
these Twitter metrics here.
Yeah, these are articles that we have published in Matter. I'm going to delete some of the audio interference just so it doesn't crash it. Give me 1 second. Okay, and you can see here, then we also have similar data on structural steel. Again, it's not as big of an issue there. See some pretty significant savings in structural steel, and the structural steel savings there's limited choices for section types, and there's some fundamental limitations related to the influence of
Hello, we couldn't hear you.
Give me 1 second. I apologize. This keeps
Okay,
dropping.
Okay, no problem.
Yeah, let me fix this. And I think there's something about the PowerPoint format it doesn't like, but I will fix this and I'll be back in 1 second.
Okay, no problem.
Okay, thank you for your patience. And yeah. Okay, so steel section, this is data provided again by CISRI, and we can look at the embodied carbon and embodied energy. This is a relatively smaller number than the rebar because, as you know, there's relatively limited section types that you can use, and there's some fundamental limitations. You cannot completely minimize the steel in a steel section buildings the same way you can in rebar, right? So the effect on steel section is relatively smaller, but still a significant amount in terms of megatons of CO2 production. Okay, so this is I think a really great story for rebar, and we published a few articles on this. Another emerging area where vanadium is saving a lot of carbon, it's a little bit more difficult to quantify, is in advanced high strength steels for auto applications. Now, there was a big push, as you know, towards carbon fibers and aluminum and magnesium, but the embodied carbon, embodied energy of these aluminum, carbon, and magnesium are very high, and steel can be fully recycled at the end of life. So I think there is a really great benefit to using advanced high strength steel. And there's expected, it's a little bit difficult to quantify because you expect not just strength and weight reduction gains, but also interesting designs that become possible by using advanced high strength steel that you may not have had otherwise. And the increased formability of HSS leads to savings by eliminating steps and reducing the amount of heat required. And so other things being equal, lighter vehicles made of HSS will be more fuel efficient and will generate less greenhouse gases, right? So this is what we're excited about. And there's really a lot of opportunities for vanadium in dual phase steel, transformation induced plasticity, twinning induced plasticity steels, and hydrogen embrittlement. So there's clear benefits of vanadium use. It's a little bit more difficult to quantify as compared to construction because of the proprietary nature of the steels and the very vastly different areas in which it is used. And so looking forward to buildings, I think we're also very excited about these very high strength steels that are coming on the market, 700 MPa, even 800 MPa steels. This is the Roche building in Switzerland is an example of this, where we are able to see some really interesting architectures that become possible when you have very high strength rebar. And the challenge is that many commercial building softwares cannot handle it. So we have had to come up with our own designs. This is an interaction diagram that shows the load bearing capacity of some of these parameters and how sensitive they are. And this allows us to start looking at this. And as you can see, you know, for 690 megapascal, we can see even a 24% savings, even above the 415 megapascal in embodied energy and embodied carbon. So, and not just the fact that we have less steel, we're also seeing in some of these new advanced buildings in Europe, very interesting architectural designs, more usable space, more daylighting, reduced bar sizes, and reduction in member sizes. We're seeing all of these benefits from vanadium microalloying, and this is becoming more and more popular. Just to give you a brief introduction to some of the work we're doing now, we're moving towards an input-output based hybrid model. Instead of a LCI inventory model that we were using, we're using macroeconomic data for vanadium and steel and such. And one of the things that has come out of this is a really great indication of how much water usage is saved by vanadium microalloying. And it's also very significant. So we end up, again, these are some examples of embodied energy and embodied carbon. And we end up seeing actually that the savings in embodied water for steel is about 6% as compared to non-alloyed steel. So there's a pretty large benefit in this. So these are some articles we have published. If you're interested, please feel free to take a look or take a picture. And these slides will also be recorded and made available. Environmental science processes and impacts. This is a article that we published that has a detailed accounting of the rebar story, the Sichuan earthquake story. I think this is an article written for the popular press, just sort of trying to explain to the research audience how Chinese rebar has really made a huge dramatic improvement in the last 15 years and how much of an amazing sort of transformation it has enabled in the Chinese construction industry and in reducing the carbon footprint of the Chinese construction industry. So it's a great story. This is in Matter, and we have recently published the Ice Science is a comprehensive look across the board at every type of application of vanadium, both in buildings, auto steels, and also in some emerging applications. And then this is our input-output model, the macroeconomic model that we've been looking at. And where we are focused at now is really looking towards vanadium redox flow batteries. This is, the price fluctuations I showed you before had a major impact on redox flow batteries, the adoption of redox flow batteries, because people really need to have stable prices for that. And redox flow battery capacity is currently still a little bit small. Vanitec maintains a worldwide database that we're helping them maintain. It's only about 2.13 million metric tons currently, but this number is going to grow. And VRFBs are a key part of coupling to wind and photovoltaic especially. And so this is an example of how many megawatts. You can see we're really poised for dramatic growth in VRFB production. And again, this is going to lead to some tension with the steel industry, but hopefully the tension will be short-lived. Hopefully there will be new opportunities for vanadium, expanding vanadium access in the industry in the years to come that will allow for some synergies between the old and the new. And this is I don't want to go over every point, but the environmental impacts have been compared. We've taken projected capacity from Guidehouse, and assuming there are some challenges with VRFBs, the capacity are relatively low, but we can quantify the benefits. And as you can see in the future, assuming 32,800 megawatt hours capacity, we're going to start to see some very significant carbon savings, especially in the scenario where there is no storage, which is really the current situation where for most wind and for most wind and for most solar, there's no storage whatsoever. So this is a database, and China is expanding rapidly in VRFB footprints. If there are anything that we encourage Vanitec members, we're working actively with Dr. Yu Li to maintain a database, and Dr. Yu Li is also a huge source of information. So please contact us or Dr. Yuli if you have any information.
So with that, I'd like to
So I'm going to
conclude,
stop here
today's
and
presentation.
thank you for. I'm happy to take any questions you might have.
Okay, thanks very much for Dr. Banerjee's presentation. His presentation, I think, included a lot of topics. As you know, life cycle assessment very important, especially I understand for steel industry people. Most people do not quite understand the real how to calculate it and the real effect in the near future for our steel industry. He also talked about a lot of such as the vanadium application in different fields. Okay, now we have 4 minutes for question or comment. Please.
Okay, thanks for Sarbajit presentation. Your presentation focused on the vanadium application in China. So my question is about that because you from the TNM taxi to A&M University. So my question is about that the vanadium application in the USA, whether it is the similar as the application in China. So could you please share me more details about the vanadium application in your country? Thank you.
Yes, thank you so much. That's a great question. So, we actually, I think China has been really a front runner in coming up with the building codes. A lot of the building here is still wood-based, and so really not so much use of rebar. And then there is also the rebar that is used and the steel sections that are used. There's still a huge reliance on QST. And there's major mills that are still doing a lot of QST. So the vanadium intensity in construction is not great. And in other advanced high strength steels, of course, you see a lot more vanadium used. I think the US is not a great case for vanadium incorporation microalloying. There's some interesting trends that are really coming true now in India, where I think India did not have anything, and a lot of the mills were QST, based. But now, as they look at the Chinese story and earthquake resilience, there is increasingly a movement towards having some standards, some composition standards, not just tensile, not just yield strength standards. And I think India will be a huge market for vanadium microalloying in the years to come, because again, lots of similarities with China. US, again, single family homes are mostly not steel frame at all, so not a huge growth area, I would say. Thank you. That's a great question. Yeah. In the US, I think I'm seeing a lot more growth in VRFBs and potentially explosive growth in automotive batteries, if that starts to take off. And that's been only last 6 months, last year, there's been a lot of consumption that is, or it's looking like it might really take off.